Have you ever considered what gives an electromagnet its incredible power, enabling it to lift heavy objects or precisely control machinery in countless applications? The strength of a current coil's magnetic field is fundamentally determined by four primary factors: the magnitude of the current flowing through the coil, the total number of turns in the coil, the coil's physical length or geometry, and, crucially, the type of material constituting its core. Understanding why these factors are so influential helps us truly grasp electromagnetism. First, the current directly dictates the field's intensity. A greater flow of electrons produces a stronger magnetic field, as current is the very source of the field itself. Second, the number of turns in the coil effectively sums up the magnetic contributions of each individual loop, so more turns lead to a proportionally stronger field. Third, for a given number of turns, a shorter coil length means a higher density of turns per unit length, which concentrates the magnetic field and thus increases its strength. Finally, and perhaps most dramatically, the core material profoundly impacts field strength. Placing a ferromagnetic substance, such as iron or nickel, inside the coil can amplify the magnetic field by hundreds or even thousands of times compared to an air core, because these materials possess internal magnetic domains that readily align with the coil's externally generated field, creating a powerful synergistic effect. Engineers leverage this precise understanding to design electromagnets for specific purposes. By carefully controlling these variables, they can fine-tune the magnetic force required for anything from delicate relays in electronic circuits to massive lifting magnets in junkyards. This practical application of principles allows for predictable and repeatable magnetic field generation. To quantify this relationship, you might encounter the term magnetomotive force, often denoted as MMF, which is the product of the number of turns and the current. This MMF drives the magnetic flux through a magnetic circuit, much like electromotive force drives current in an electrical circuit. Furthermore, the concept of magnetic permeability, a property of the core material, explicitly describes how well a material supports the formation of a magnetic field within itself, providing a direct measure of its amplifying capability. By appreciating how current, turns, geometry, and core material interplay, you gain the foundational knowledge to design and analyze electromagnetic devices. This allows you to not only predict a coil's magnetic behavior but also to purposefully engineer coils that achieve a desired magnetic field strength for innovative solutions across electrical engineering.